All right, class, welcome to section 4.4. So the background idea here is, just as we looked in chapter 2, and we looked at minimums and maximum values of a function, that's the same idea here. So just to review a little bit, in chapter 1, again, we learn about derivatives and we learn what they mean and what they measure. So we learned that the derivative of a function measures the slope of the tangent line to that function at that specific point in time. And then we explored that further in chapter 2, and we saw that clearly anytime the tangent line has a horizontal or is horizontal, right? So it has a slope of 0, that must mean that you possibly have a local maximum or a local minimum in the graph of your function, right? And then we put those mins and maximums to good use, and we call that optimizing or optimization of functions, right? Optimizing, one more time, meant to find minimum or maximum values. The other thing that we also learned is that sometimes, even though you have a horizontal tangent line, yes, so the slope is equal to 0, that doesn't mean necessarily that you have a minimum or a maximum. It could very well be that the graph is just simply evening out there, right? But it continues to grow, right? So we put those few ideas to good use. First of all, look at where the tangent line is horizontal, so where the derivative is equal to 0. And then we also looked at the fact that sometimes the derivative could be undefined, yes. And again, that's because your graph maybe comes to a corner point, and that could still be a minimum. But then we call those the critical numbers, yes? And we said that if you have a min or a max, it's amongst one of these critical numbers, right? That we turn points in a bit. But that not all your critical numbers or your critical points are necessarily mins or maximums. But if you want to find them, that's where you have to look among. Okay, so that's the same exact idea for functions of multivariables, right? So we learned in the last chapter, or in the last two sections, how to take a first derivative, yes, a second derivative, and beyond. And then now we just want to put that to good use. So as I had said, as we looked at and saw in section 4.1, the graphs of functions of multivariables aren't as easily obtained as if you have a variable only, right? So x is your variable, the y value is already the function value. Now, maybe just in the case of a function of two variables, right? You already have a three-dimensional picture. This is a two-dimensional picture, right? It's got the two axes. So x and y are just your input, and then z is the output of that function. So it creates a three-dimensional picture. So as I had said, we won't be able to graph these, but at least we can kind of take a look at it. So let me use a pencil for this one. So here it is. Look at this graph. Sure enough, it's showing us that this graph here has a maximum, right? Maybe it's a local max, maybe it's an absolute max. I mean, we only have this little piece. If that's all there is of this graph, then this local maximum is also an absolute max. And as you see, here is this should be the x direction right here. It's missing an x. So in the y direction, there is a maximum, right? And in the x direction, there is a maximum as well, right? So there's a max in the x direction. That simply means the fx must equal to 0, right? So remember how when we talked about partial derivatives, we said there's a derivative in the direction x, and then there's a derivative, a change in the direction y, right? So we keep one variable fixed and we only let the other variable change. There's a max in the x direction. There's also a max in the y direction. So that must also mean that fy is equal to 0. All right. Now, if you look at this picture here, same thing. In the y direction, there's a horizontal tangent line. In the x direction, right under there, there's a horizontal tangent line, and it's a minimum value in both directions. So it's a minimum in, and I'm not going to write it again. It's the same thing here. In the f direction, here, maybe I should make these this way. It's the same thing. Okay, so the derivative with respect to x must equal to 0, and the derivative with respect to y must equal to 0. So sure enough, you're going to want to find your critical point. You're going to set the derivative equal to 0. Which derivative? The first derivative, yes? Except for, as we saw in the case of a function of multivariable, there are multi-first derivatives, right? So there's one for each variable that function depends on. Okay. Now look at this picture right here. A saddle point. What's a saddle point? Well, as you look at it, what does the derivative in the y direction look like? It's right under here, yes? Under this graph. So it's basically under this shape, right? But it's definitely horizontal, yes? Okay, so what about the x direction? If you're looking at the x direction, you're actually on top, exactly on top of the curve, okay? So sure enough, we have a maximum in the x direction. So fx will have to equal to 0. But if you look at it, you have a minimum, right? It's the lowest point in the y direction. So fy must equal to 0. So it seems to me that it's the same conditions, right? And there you go. You have a derivative that equals to 0 at both x and y, and yet you don't have a maximum or a minimum. It's what we call a saddle point. So it's almost the idea here. The derivative was equal to 0, yes, but you didn't get a maximum or a minimum. So it's a critical point. So not every critical point, in other words, what we'll be looking at when the derivative is equal to 0 would lead to a minimum or a maximum value, right? Just the same. So this is called a saddle point. So again, just picture the bridge or the space between your knuckles, right? In this direction, it's a lowest point, but if you turn your knuckle this way, in this sorry, off camera. In this direction, it's a maximum point, right? It's the highest point looking this way, but it's the lowest point looking this way. That's called a saddle point. All right. Now, this should be quite clear and straightforward that a local or a relative max or minimum, it simply means that what? You have a maximum at a point if what? The function value at that point is higher, right? It's more than the function values at all the points around it. Yeah, so it's the highest point, the highest function value that you get for compared to all the points around it. And sure enough, you have a minimum if what? F of, at this point AB, if f of AB is less than f of xy for all the points xy near AB. So remember, xy is now just your input, right? Before it was just an x, but now xy is your input. So in other words, what? Any point xy that you put, this one here creates the lowest y value, right, of all. Okay. All right, so that's easy and straightforward. Okay. What is a critical point? Same thing. Same exact thing that we learned in chapter 2. A critical point is where what? The derivative is equal to 0 or it's undefined, except for if you have a function of 2 variables, how many first derivatives will you have? You will have 2 first derivatives. And sure enough, let me just put this aside. If you have a function of 3 variables, yes, then to have a critical point, what's going to happen? All 3 partial derivatives will have to equal to 0, right? So the first derivative, no matter how many of those you need, will all have to equal to 0, yes? Okay, so just as before, if you're looking for local mins or maximums, they can only occur at a critical point. So though just as before, not every critical point is a local or relative min or max. But if you want to find them, that's where you have to look for, right? So some, as we just saw, some mins or maximums could just be saddle points, yes? Okay. So we will find a method in this section of how to tell if you have a min or you have a maximum. We'll get to that. First things first, let's just practice, same as we did in chapter 2, on finding critical points for the function. Remember, this time a critical point is just an xy. It's like the, I'm just going to say, the equivalent of a critical number in chapter 2. Does that make sense? Okay, so now your inputs are points, not numbers anymore, right? Because you need an x and a y value. So this should be easy. How do we find a critical point? Well, we're looking at simply where the derivative is equal to 0 or it's undefined. Fine. What would be the first derivative? Well, the first derivative, we got two of those. So fx is 10x, right? Plus 4y minus 32. Okay. We have a second first derivative, fy. That's no y here, so that's negative 6y plus 4x, and then plus 10. Okay, so what did we want? We wanted both these derivatives to equal to 0. Okay, so what this leads me to is what we called a system of two equations in two variables. So you've done these in your elementary, yes, algebra classes. You've been dealing with these kind of systems for a long time. What I'm going to do is nicely rearrange them for you, and then even more so, it would look like a familiar system of 2 by 2, right? Linear equations in two variables. Okay, so I rearranged them, and then do you remember how to solve them? So what we did is we wanted to make sure that either the x or the y cancels out. So one way to achieve that is to maybe, if you want to get rid of the y variable, I could multiply the top equation by 3 and the bottom equation by 2. Yes, 4 and 6 both go into 12. That's their common multiple. So 4 times 3 gets me to 12. 6 times 2 gets me to 12. But I want one to be a positive and one to be a negative. So let me write the new equations down below. So the first equation becomes what? I multiply everything by 3, yes? So that's going to be a 30x plus 12y plus 96. This one's going to be an 8x minus 12y equals to negative 20. So don't forget to distribute nicely, multiply everything by it. So adding these up, I'm going to get a 38x equals to 76. So it comes out nice, it's supposed to. Dividing both sides by 38, that's exactly the double of 38, so x is 2. Okay. All right, so what do I do once I found the x? That's just one of the input values, right? I also need to find the y. So we're going to take this x and put it into either one of these equations, no matter which one you pick, to find the y value. So I don't know, I'm just going to pick that first equation. That says 10x, so 10 times 2 plus 4y is equal to 32. So that's a 20, which I'm going to minus over. So 4y is equal to 12, which means easily y is 3. Okay, so that's what we found out, that the critical point is 2, 3. There's only one. Now, will this 3, I'm sorry, what did I do? I did write 2, 3, and I said 3. So the critical point is 2, 3. Be sure to list the x first and then the y second. So does this critical point lead to a minimum, a maximum, or maybe neither, right? Maybe it's a saddle point. We'll see how we'll decide on that. But That, again, it's not as easy as if you just have one variable only and you only get to solve one equation in x, yes? Now you have two variables, so you get to have two equations, right? And solve for both x and y. Okay, now I'm not going to even talk about functions of three variables, all right? I don't think there's any reason for it, but we could possibly if we had to. Okay, so this is the method. It's a long way, okay? But we're going to go over it. So how are we going to find out if a critical point is a minimum or a maximum? Well, same as in chapter 2, we didn't quite use much that second derivative test. Especially for those word problems that we had to do. It said find the minimum, and I said you don't need to bother. If it says find the minimum, the critical point you found is a minimum. But if you wanted to truly check, what did you have to do? You have to look at the second derivative. So let me just put this aside. What did we look? We found our first derivative, yes, set it equal to 0, and out of that we found all the critical numbers, right? So a bunch of x's. Okay, and then what did we do? We found the second derivative, yes. And then we plugged in all these critical numbers that we found into the second derivative. And we said that what? If the second derivative at that critical number was positive, what did it mean positive? It means that around that point, the function was looking up, right? It was concave up. So that means that critical number was a minimum value, yes. Now, if the second derivative at that critical number was negative, what did that mean? It means the function was concave down around that point, yes? So that critical number was a maximum. So all you had to do is check the sign. So the same idea is going to happen here. The first step definitely is to do what? Same as before. Find the critical points, yes, those critical numbers for the function. All right. Now, once you have them, what do? You have to plug them into the second derivative. The problem is, though, what? If you had a function of one variable only, how many second derivatives did you have? One, yes. All you had to do is plug it into that one function, see if it's positive, yes, or negative. That's all you had to do. Now, how many second derivatives do we have for a function of two variables only? Now, we definitely went through that in 4.3, and annoyingly, we found out that there's what? 4 second derivatives. So we need some kind of function. I'm not going to plug them into all 4. One will be positive, the other one will be negative. So that's crazy, yes? So what we do is we come up with a function that involves all 4 of them. We call this the D function, and we are performing what's called the D test. Okay, so it seems quite involved, but it's not that bad. The only thing is that, again, since we have 4 second partial derivatives, we need a function that incorporates all 4. Okay, so all I'm doing is simply what? I'm just going to write it out, maybe easier. It's simply fxx times fyy minus, so the ones that are the same, minus really fxy times fyx, so the alternates, okay? Now, of course, what did we learn? That fxy is the same thing as fyx, right? You don't have to find both. So this is why the function says just find one of them and square it. But really, that's what it is, right? So you multiply the 2 that are the same minus the 2 that are alternating, right? Okay, so that's the D function. Okay, so that's kind of like your second derivative function. So all I'm going to do is what? I found my critical numbers, right, which now they're called critical points. And then what do I have to do? I have to plug them into this second derivative function, yes? And then decide, is it positive, is it negative, and so on and so on. Unfortunately, that's not all that easy. So this is what the D test says, that if this value comes up to be positive, yes, Doesn't mean you have a minimum, in fact. If it's positive, you know you found a min or a max, okay? To decide if it's a min or a max, you have to look at the sign of fxx only, and I'll explain why. Now, if fxx is positive, right, and of course d itself was positive, then you have a local min. So positive, this fxx is a positive, then you got yourself a minimum, yes? Now, if fxx is a negative, I'll write it again here, then you got yourself a maximum. Yes, so a negative fxx is a maximum. Okay, but so that's it. So if this d value comes up positive, you know for sure you're a min or a max, right? But which one it is, the tiebreaker, comes from just looking at fxx. Okay, now if this value comes up to be negative, right, so if that d value is a negative, then what it means is that you got yourself a saddle point. Okay, so that's that third situation, right? I'll bring back that picture. So we don't have a min, we don't have a max, we have a min one way and a max the other way. So you got yourself a saddle point. Now, if d should come up to be 0, which is not going to happen in the problems we'll be looking at, but just so you know that if it should come up to be 0, I mean, it's a difference, right? Of two values, why wouldn't it be 0? But so if it does, then we say the test is inconclusive. Okay, there could be a min or a max or neither. We don't know. We need to perform more testing. But sure enough, that won't happen in our class. As I said, for a calculus class, yes, that's going to happen. So let me bring back our first picture. Oh, if I can find it. Yes. No, I cannot find it. Where did it go? Oh, no. Where did I throw it? Yes. There you go. Here it is. So, why does this work this way? As you saw, if you have a maximum, yes, it's a maximum this way and a maximum this way. Basically what? You have a sad face going in an x direction and you have a sad face going in the y direction. So it's kind of like two minuses make a plus, right? So that d value multiplies the fxx and fyy, right? So that's why we say if you have a positive d, that could be because in both directions you have a max, yes? So then we don't need to look at both fxx and fyy. If it's a max one way, it's a max the other way, right? So again, that d value could come up to be positive, yes, from what? Oh, geez, oh yeah, the two minuses, yes, because they're looking both way down. In a minimum, what do you have? You have a concave up in a y direction and you have a concave up in an x direction. So you got to multiply two positive values. So that's why that d came up to be positive. You don't need to look at both fxx and fyy. If one of them is positive, right, then you got yourself a min, right? So that's why it's just enough to look at fxx. But if that d value came up to be negative, why? Because you multiplied a positive to a negative, yes? In a y direction, you had a smiley face, right? So fyy was positive, yes? In the x direction, you got yourself a concave down, right? A sad face. So one partial derivative was positive, the other one was negative. So you know for sure you got yourself a saddle point. Now, it didn't matter which one's what because it's neither a min nor a maximum, yes? So that's why we're looking. If d comes up positive, then you had the same sign, right? Going both ways. So you just have to look at, are they both negative? Were they both positive? Is just enough to look at one, right? That's why we just look at fxx. If that d value is negative, then you got yourself a saddle point. So it's neither min nor max. There's no reason to look any further. Does that make sense? Well, I can't hear you, so I'm going to pretend you said yes. All right. So let's move on and see about this. So we already looked, it said, find the extreme relative values of this function. I'm going to stop this video and I'm going to continue. It's getting too long to upload, so I'm going to continue in the next video.